So as you, well, I think everyone knows, I'm associate professor at the geography department, been here for now 5.5 years. I run the surface dynamic modeling lab, which we have a few members here. And yeah, so what I want to do today, with these kind of talks, there's always this balance, right? Whether you dive into one topic and spend an hour talking about it, or what I think is a better use of this specific opportunities to give an overview. Also, I get excited about a lot of things, so I kind of hate to just focus on one thing. But as a result, I'm not going to dive into a lot of things. So if anyone wants to talk to me after that on some specific topic that I'm going to talk about, then yeah, I'm always happy to talk about research with anyone. Also, so because we have almost all of our students from the lab here, I want to apologize to you if you're not mentioned there, because there's a lot of great work that's done, but not a lot of time to talk about. So I'm going to talk about two main topics that are the main research emphasis that we have in the lab. The global river modeling that we've been doing for quite a few years now, and then flood mapping and analysis, which is relatively new, a newer kind of research topic that we've been working on, to some extent related to the National Water Center work or emphasis and so on, but I'll talk about both of these. So I want to give, I'm going to start with the global river modeling. I'll ask you a question. Can anyone guess which river is that? That's a Google Earth image that I took. I really like it, actually. Who said Amazon? There you go. Correct. So this is the Amazon River, my favorite river, obviously. There's some cool stuff here. You can see the Andes at the, far to the west. You can see the Rio Negro River here, which is a very low sediment concentration river. So the confluence between the Amazon and the Rio Negro is a very interesting one. I'm going to show a slide a little bit later about it. But I just really like this view, and this is a Google Earth engine, right? So it's a very easy thing to generate yourself. So I don't need to spend a lot of time convincing people why rivers are important, not in this venue. But what's going on? I mean, global freshwater systems are undergoing quite a rapid or quite a lot of stress from human development, or what we'll generally define as anthropogenic activity, right? There's more people developing economies or emerging economies and so on. Their development is accelerating, and as a result, there's more and more stress on freshwater systems. At the same time, we have climate change, which also introduces its own modification or in some cases stress, and in some cases even increase in water in some locations. So the two are not obviously acting in complete isolation, but they have a very interesting and especially explicit dynamics between them on a global scale. So as a result, the argument that I'm trying to make is that developing and using and analyzing global scale rivers is actually quite an interesting and worthwhile and timely undertaking, which is basically what we do. So I'm kind of trying to frame where we're coming from for doing the global scale river modeling that we do. So a few years back, this is the first paper that was published on this model. It's called WBM SED. WBM stands for Water Balance Model. SED stands for sediment, and this came out actually, this was actually one of those weird cases. The paper was actually accepted in 2011, but published in 2013. It was part of a special issue, so it was waiting for, anyway, never mind. But so it's been around for a few years now, and I want to give you a very quick overview of this model. It's based, the underlying framework is called WBM Plus, which is a global hydrology model that actually not a lot of people have heard of. So everyone knows VIC, right? But WBM Plus has been around probably quite as long. They started developing it in I think in the 90s, and it's undergone a lot of developments, and I think it's actually superior to VIC and many other frameworks because it incorporates, embedded already a lot of the processes that are extremely important in kind of large-scale hydrology. So this figure over here, they tried to kind of summarize this. I took that from their actually old website. So them, I mean, there's a group of scientists, initially were in the University of New Hampshire. Most of them then moved to the City College, New York. So Charles Horace Marty, I don't know if anyone heard of that name, but he was the PI on a lot of these efforts. And but the nice thing about WBM Plus is that it can do reservoir, it can do irrigation, shallow groundwater, water uptake from rivers and groundwater. A lot of these processes that a lot of the other frameworks don't really have embedded in them. They are sometimes add-ons to, and it also do it's not just a surface model, Earth surface model. It also have a water routing mechanism embedded as part of it. So it's a very nice, and it's actually now undergone very significant modification. So it's now also very computationally efficient, and it has a very large input data set and a lot of options for modules and so on. So in a nutshell, so the underlying hydrology model, that's someone else developed that. We just used that and added to it. One thing that we did incorporate in the what we call WBM SED, which is the sediment component, is this, which I'm actually quite proud of. That came out in a later paper, that what we were trying to do is to think about flooding and how flooding is influencing global hydrology or water transport in rivers. Pretty much all of these models, including the national water model and all of these, they don't have capacity on how much water a river can transport. So if you give it enough rain and enough water, enough runoff, it will transport an infinite amount of water, which is obviously not realistic, right? Because real rivers, once you have too much water, they start moving, or the water starts moving to the floodplain, and that mitigates that hydrograph, basically. So me and my colleague developed a very simple approach to try to think about when do these processes happen. So we came up with an estimate of bankful discharge based on some global hydrology, hydraulic geometry estimation that were published at the time. And therefore we can mitigate that flood wave, and we can also think about sediment storage on floodplains and so on. So that was my contribution to the hydrology part of this model. So the main contribution was then on the sediment part. So that was what I initially developed as a postdoc at the University of Colorado with James Savitsky and Albert and others. So we incorporated a semi-empirical sediment flux that was developed by Savitsky and Milliman in 2007. What we did, we came up with a mechanism to calculate that semi-empirical equation from basin outlet, which is what they did, into a spatially explicit framework, which is what WBM is. As a result, we can have a good, well, sometimes good, sometimes less favorable estimate of sediment flux on a daily basis in every location on Earth. This is, to the best of my knowledge, one of only two global sediment flux models. Maybe there have been newer ones that I'm not aware of, but at least at the time that there were only two of them. Now, one new development that we had, I got this NSF grant, I guess it was 2 years ago now, to incorporate bed load. So the previous slide talked about suspended sediment, which is in a way an easier thing to do. Bed load is quite difficult because it's such a dynamical, well, even in lab analysis, it's a difficult problem to solve. So we came up, or we proposed an approach to use an existing simple bed load equation, the modified bed load equation, and that's something that's following Katner and Savitsky in 2007. And we are now, so Tazmol is the graduate student that work on it, and we are now trying to validate the model. That's where he is right now. So Tazmol was very instrumental in developing a data set, a global bed load data set that we can compare the model against, and we'll see how we do, hopefully not too bad. We're counting on you. Now this, whoa, what happened to this now? What made this happen, one of the big problems that we have, because this is not a very difficult equation, especially if you simplify it, which we do, one of the difficulties that we have is that bed load is directly linked to the slope of the river. So we have basically, we can minimize this equation into slope and discharge as the two main parameters that vary in space and time. So discharge we can do very well with the model, right? That's easy. But slope, that's actually pretty difficult to do for rivers. Now we all know, or most of us, or most of you probably know, that slope calculation is actually pretty simple. You take a DEM, you put it in ArcGIS or whatever GIS, you click the slope tool and you get slope estimate, right? It's really easy. However, these kind of algorithms don't work well at all for river location because the river slope is extremely low. Like if you look at the Mississippi, the slope there is, at the downstream end is 0.000002%. So it's a very, very small value, and therefore DEMs, traditional DEM, even if they're at high enough resolution, they can't really give you a good estimate of river slope. So we came up, that was a graduate student, Tong Wen, she finished in 2016, and she kind of tested a global river slope map that allows us then to do the bed load, hopefully in a good way. Another, it's actually not recent anymore, but we didn't publish it yet, that's kind of a lesson when you're trying to do multi-collaboration with people from all over the country and you don't have any funding to do it, it can drag for years and years, which is the case here. So maybe some of you have already seen this slide on different presentation. So this is an attempt to extend the model to do nutrients, in particulate nutrients, nitrogen, phosphorus, and organic carbon. And that's because Mayorga and others have developed a global model in which these specific nutrients and organic carbon are linked to sediment concentration. So they come up with some equation, which are here, also kind of semi-empirical, not too difficult. So if we have sediment concentration from the model, which we do, it was pretty easy to incorporate this procedure into the model and then come up with these estimates. And we actually did some validation. It looks pretty decent. The problem is that okay, so when it comes to global validation of models, when you do water, you're okay, right? There's pretty decent amount of observations of water around the world. When you do sediment, it gets much harder because it's really hard to get sediment data outside the US. When you do nutrients, it's just a nightmare because it's all over the place. Everyone, measure in a different way, and it's very sporadic and it's very local, usually small streams and so on. So we did some initial estimate, looks pretty good. We need to publish this at some point. So now we do have that capability of doing particulate phosphorus, nitrogen, and organic carbon at the global scale in a spatially explicit way. So, so just to wrap up the kind of the introduction to the model, the global model. This is just a map, just from one of my, I guess, publication. And it shows you kind of the scale of it. The model itself, WBM said, we simulate on a daily basis. We usually analyze it kind of either monthly, yearly, or long-term basis. We can go back to 1900 all the way now to 2016, and now even predict into the future using GCM data. That's something that Nishani is going to do as part of her master thesis. And actually, this is not true anymore. That runtime. As I said, the model has undergone considerable modification to its framework, so now the runtime should be, if it works properly, I'm still working on that, maybe even half an hour for 1 year of simulation at 6 arc-minute, which means that we can go into higher and higher resolutions. So we use 6 arc-minute. It's actually fairly high resolution for global modeling. 6 arc-minute is about 11 kilometers by 11 kilometers at the equator grid size, so it's actually pretty high. We tend to mask, as you see here. So we actually calculate everything on a grid by grid basis. So every grid on the land will have an estimate We usually mask out all the small rivers because the confidence in sediment predictions for these small rivers is pretty low. So that's what you see here. We basically remove, or we don't show, any of the grid cells that are for rivers with less than 30 cubic meter per second discharge on average, and less than 20,000 square kilometers in contributing area. And this is just an example of doing high resolution. I don't know if it comes across very well in the projection. You can hardly see the rivers. This is using 15 arc-second simulation of Northeast US. So you can definitely do these more regional, higher resolution modeling. Now this is kind of this eye candy that I like to show. This is that Rio Negro Amazon conference that I was talking about. You can see another Google Earth zoom in. Again, I hope it comes across. So this is the Rio Negro coming here, and it's very low sediment concentration. It's very clean of sediment, and then you have the Amazon that kind of drains the Andes, and this confluence point is actually a very famous tourist attraction in the city of Manaus, because you can actually see that mixing front between the two, and that mixing front can go for 100 kilometers or even more. Yeah.
That's exactly what I was going to say. I saw some pictures. They look really amazing.
Yeah, there's even differences in water density, differences in temperature. It's a real thing. So it's one of the most extreme example of a really interesting confluence. Anyway,
I think the sediment from one river is yellowish and the other one is like kind of dark.
yeah, it's very dark because there's almost no sediment,
Yeah.
and the pH is different. It's a whole thing.
Very strange.
So I like to show this because the model is actually doing a fairly good job at predicting that differences in sedimentation, in sediment concentration. Here, this is showing sediment concentration for the Amazon basin, and also give you a zoom in on this beautiful basin. All right, I want to talk about some case studies that we did with this model, and there's quite a few. So I'm going to talk about just 3 of them, I guess, 2 or 3 of them. And one thing that I've been very interested in the last few years is anthropogenic impact. So how do humans impact rivers, global rivers? And it's especially when it comes to sediment, it's a very interesting case study, because we have 2 types of contrasting influences when it comes to human activity. One is increase in sedimentation, right? Because we disturb the land, right? Agriculture, construction, mining, and so on. So we introduce a lot of sediment into the environment, a lot of sediment that ends up in the river. So I call it the busy ant syndrome, right? We're very good and very effective at moving and disturbing sediment. On the other hand, we are also very busy beavers, right? We put a lot of dams on rivers. So there's a very contrasting mechanism that's going on. So what is the net effect, basically? What's going on here? What is the total effect of human beings on sediment in global rivers? So people have been interested in that for quite a number of years. So there's been an estimate. So Boris Marty in 2003, he estimated that the net effect of anthropogenic activity is a 30% reduction in sediment flow to global oceans. So even though we disturb the sediment a lot, the dams are so efficient at trapping sediment that the net effect is a 30% reduction. Dole he tried to estimate, or they tried to estimate, how much water, or how much more or less water we get to the oceans from river, and they estimate a pretty mild 3.5% decrease in the amount of water that reach the coast. And that makes sense, because even though you put a dam, that dam doesn't really stop the water indefinitely, although you do use it for irrigation and so on. But the net effect is not that great. At least that's what they estimate. So this is the WBM SED model is actually pretty much a perfect tool to do this kind of experiment, if you trust it, obviously. Well, I shouldn't say perfect. There's nothing perfect, right? You don't account for all the processes. But it's a really efficient, let's say it like that, tool to do that, because we can switch on and off the relevant processes in the model, and therefore do these experiments actually very easily. So we call it pristine mode. So we can run the model in pristine mode, which will affect the relevant parameters, including water discharge. So the model, as I said, has irrigation, have water uptake from groundwater, from rivers, from reservoirs, it has dam and dam operation and so on. So we can switch that off in the model and change the hydrology, and we can also switch off the relevant anthropogenic factors that affect sediment. So basically what we do, we run the model on pristine mode, right, without all these anthropogenic impact, and we run it with what we call disturbed mode, with everything included. This is actually come up of a thesis by Sean Carter, is now at the National Water Center. I write here in prep. That's wishful thinking on my part at this point, I think. Anyway, but what he did, he did a really nice thesis actually, I thought. I don't know if he agrees, but I think he did. He developed land use parameter into the WBM SED model. Before that, there was some very generic anthropogenic impact on sedimentation. He introduced spatially temporally explicit land use into the model. And what he's done here is to look, okay, what happens if I switch off the land use component, right? What is the importance of land use into the model? So in this case, right, he looks at the simulation with and without land use, and you can see it's very diverse. We're just focusing here on Asia. So some rivers, you see India and so on, a very significant increase, right? A lot of pressure, socioeconomic pressure in China, some and so on. In some parts, you go to the Arctic, there's not a lot of people living there, there's not a lot of anthropogenic activity when it comes to land use. So you can come up with some, if you want to summarize it, which he did on a continental basis. He found this kind of, I don't know if that's a realistic number, but at least what the model tells us is that land use alone can contribute over 100% of increase in sediment in Asia. And in other places, it varies a lot, right? So South America, it's only 8%, so it's a really, very diverse and very heterogeneous response. Now, what he did next was, okay, let's add dams into that, right? Because we said we have these two contrasting factors. So now this is just, again, Asia, and this is when you introduce both dams and land use. And as you can see, they still see a lot of increased sedimentation. Now the scale, the color scheme here is a little different. And as you can see, also did categorical changes instead of a continuous one. But again, we see the Indian subcontinent, we still see a lot of increase. Some other parts, China, right, has been very active in building those large dams. So we see a very significant decrease. And when he sum it up, the result at least tells us that Asia is neutral, meaning while we get a lot of increase in sedimentation, especially in India and so on, but there's so many big dams going on, or so much damming going on that the net effect is zero. That's pretty much what the result says, and it varies a lot between different continents as well. And the total value, I guess I didn't summarize it, but but the total decrease in sedimentation was actually very, very similar to what Vorismardi, for example, predicted. So we find as well about 25 to 30% decrease globally of sediment going to the oceans due to anthropogenic activity. Now I'm going to go about, this is a different case study, very recent. There's a paper under review right now, a group from, so Francis Dunn and Stephen Derby, both from the University of Southampton in the UK. And what they did, they used the model, or we used the model in a, I thought was quite interesting way. She was looking into the future. Francis was at the time a PhD student. She was looking into the future. She was interested in the future of deltas. And she was looking into the future using, as you can see, 4 RCP, so climate projection. So she was using GCM projection into the future of climate, running the model with that, and 3 different socioeconomic scenarios that I forgot where exactly she took that specific scenarios. So she was trying to say, okay, what is the future of deltas going to be in terms of how much sediment they're going to get? She was particularly interested in deltas. That group is very strong on tropical areas and deltas and so on. And she ran the model with all these different scenarios, and this figure is trying to summarize her conclusion. I'm not going to spend a lot of time on it, but generally she finds that most deltas, most big deltas, are going to see a significant reduction in sediment in the future. Again, this is trying to kind of take into account all the different scenarios. So it's a much more complex study. I'm really summarizing it into the nutshell. But yeah, that's not very surprising, especially considering the case study that I talked about before, right? We are very efficient at putting dams. The future, it looks that we're going to have even more dams, especially in developing countries or emerging economies, China, India. So in the US, we actually do see, you see the Mississippi here, we do see some increase in sedimentation. I suspect, I don't remember or don't know, I should say, I don't remember because I really don't know what was the leading cause of that, but you can imagine that in developed country, we will potentially see an increase because there's a trend towards less river engineering in the US and in Europe. Now this is a very recent, we just presented this at AGU. This is more or less the same group. So Julian Leyland is another guy from Southampton in the UK. And they are very interested in tropical cyclones. They did a lot of work in the Mekong Delta and the Mekong River. And they were very curious to see if they can extrapolate their methodology into a global scale using the WBM-SED model. So what we did was actually pretty simple when you think about it. You take all the tropical cyclone tracks that you have going back to the 1800s, and the way they do it, they take a buffer of 300 miles, I think, or kilometers, and they remove all the rain that happened for that day around that track of the tropical cyclone. And so you can produce a rainfall data, a precipitation data that exclude, kind of take out the tropical cyclones. So remove their influence on the run. So then you run the model with cyclones and without cyclone, and therefore you can isolate the contribution of tropical cyclones on sediment flux. They have actual measurement or estimates, very high resolution for the Mekong. So this is sort of where we are at the moment. This, I don't know if you can see actually the map itself, but you can see basically it's a spatially explicit estimation of what is the contribution in percent of tropical cyclones on the long term on sediment flux in all these rivers, and obviously you get it's kind of the bullseyes is where you actually have tropical cyclones, right? You see Australia, quite significant, and this is for water, this is for sediment, I should say, and they look very similar because really what's driving sediment in this experiment, or the differences are water discharge. So we come up with some, the initial estimate that tropical cyclones contribute 17.5 billion tons of sediment to the oceans. I don't know if it's a realistic assessment at this point. Over what period, I forgot, but maybe probably the 30-year simulation. We are at the process of really start to evaluate and change it, because one of the concerns that I had going into that is that the model is not sensitive enough to really capture the influence of these extreme events. Because when you get a significant typhoon, for example, that will do more than just increase water discharge. There's a lot of bank erosion and all these other processes that the model really doesn't take into account, so there may be some adjustments that need to be done. But first of all, this was the most beautiful poster I ever seen in AGU, and I kind of kicked myself for not taking it because he just left it there and they throw it away. It was all black, so I think this probably cost them a ton to actually print that. Anyway, this is another example of the model used. All right, almost perfect timing. So I want to now move to the second topic, which we do a lot of work at, which is flood mapping, and it's supposed to say an analysis, and that kind of got blown away there. The first thing, many of you probably heard about that. It's what we call the U.S. Flood Inundation Map Repository. This was a short one-year project that was funded by the National Water Center through the UCAR Comet grant program, outreach, whatever they call it. And what we did was we were trying to fill a data gap, basically. When I got involved with the National Water Center and saw what they were kind of pushing for, these hyper-resolution flood prediction. One thing that was actually surprising to me, that there's no repository out there that actually provides flood maps, actual observational flood maps. So if you don't have observational data, how can you calibrate and validate your model, your predictive model? And that's one thing to kind of disregard that when you're doing, kind of scientific experiments, but when you're doing predictive framework, or you're trying to predict stuff or forecast, that's the word I was looking for. When you're trying to develop a forecasting framework, if you don't get it right, the whole thing is a waste of time, right? Because people will stop listening to you and will stop taking attention, and no one will use it. So that's a gap, a data gap that we were trying to fill, and we got this short grant. And basically what we did, we started mapping floods using remote sensing analysis. We have at the moment about 40, I think even over 40 at this point, flood maps all over the US, because this is a US-centric thing. And we developed a web interface. The philosophy behind this, or the idea behind this, is to make it open, completely open, no need for a password, no need for anything. You just go to this URL and you can start viewing and downloading the maps. So that was something that for me was very important, because you all know how annoying it is, right? You want to get some data from somewhere, create an account, blah, 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 and then you wait for an email and you forget the password. And anyway, try to get away from all of this, just completely open. So we have this map interface. This is, we went from Google Map embedded into ArcGIS Online, and now back to Google, because ArcGIS Online was actually less user-friendly, I thought. So people can zoom in. I'll show you a zoom in a minute, but there's also a table that has a download button next to it, and you can just go and download that layer. So this is just a shape file. So here's a zoom in on one of the maps. This is one of the earlier maps. So what I like, or what we try to do here, is really make it very, very useful and easy to use for the potential user, right? So once you click on a map, it will open this side panel here, which will give you a download link for the shapefile itself, a download link for the DEM for that location, and then a link to the nearest USGS gauging station, so you can even retrieve the hydrograph for that specific event. And also, of course, some metadata and so on. So we think of it as a one-stop shop for modelers to do that. And there's some people that started using it. Sarah has used it. Some folks at the Water Center, some folks at NCAR told me they used it. So we don't really, because we don't ask for password, we don't really track who uses it. So some people tell us that they did, so we know, but other than that, we really don't know. I guess that's the downside of making it super open. Now, I've been involved with the Global Flood Partnership in the last year, I suppose, a little bit more than that. This is an initiative that basically gets folks from all around the world to provide services or to help when there's some flooding going on, some crisis going on somewhere in the world. So it's especially useful for developing countries, right, that they don't have their own National Weather Service or mechanism to really forecast and map floods. So as a response to that, we developed the Global Flood Inundation Map Repository, which is basically taking the same repository, but we also have one flood at this point in Bangladesh. So it's a global in respect for the fact that we have one flood outside the US. We have no funding for this, so it's like, at the time there was a flood in Bangladesh, and I asked, was it you, Danuk, or?
No, I think it's a Brad.
I think it was
Brad or James.
James did that. We said, can you see if you can map the flood in Bangladesh? And he did. so we added it here. At some point, we will probably expand this, but as I said, it's not funded, so. Now, but it is a nice, I think, framework to move it forward and to add in more data like high water marks from the USGS, adding floodwater depth, which I'm going to talk about next. And one thing that especially was becoming apparent to me after the Hurricane Harvey, and so these are maps from Hurricane Harvey, flood maps that by the Dartmouth Flood Observatory, and you can see Houston here. This is a kind of Houston area, and this is zoom in on Houston. That's kind of the dark green, and you can see all these points here. These are high water marks that the USGS collected. I don't know if you can see, but there's actually no water, flood water here. So even though we had a lot of data during the events, SAR data, aerial photography, even JPL, UAV SAR, and they were not able to produce good flood maps for Houston. And that's because doing flood mapping in urban, such a dense urban area is very, very difficult. And so we are trying to get someone interested in maybe funding some project that actually start to look into this kind of augmenting remote sensing analysis with other modeling and the terrain analysis to improve that, because I don't think we should just accept the fact that we can't do this properly. So anyway, that's sort of where this is going. And the next thing I want to talk about is actually one of the more satisfying projects that I had, I think, in my career, because it was it started and ended in a publication quite quickly, and also to me it felt that it's making quite a bit of an impact, and it's I just enjoyed working on it. So this is we call it the floodwater depth estimation tool, and it's very new. The paper just came out in December, and basically what it is a conversation that I had with the head of the Dartmouth Flood Observatory, who told me that, you know, a lot of folks use our flood map, remote sensing flood maps, but they also want to know how deep the water is, not just where it is. And he said, do you think we can do that? And I started thinking about that problem, because we have DEMs everywhere now, right? There's global DEMs, the resolution is increasing all the time, so we have good data and it's very accessible, unlike even just a few years ago. So if you have a DEM and you have the area of the flood, there must be a way to calculate how deep the water is. Initially, it felt like a very simple problem, and then, okay, that's the paper that came out. And if you simplify it, you think about a cross-section of a flood, right? So you have, this is your typical water level, and now you have flood water. If you kind of simplify this problem at the cross-section level, if you know where the water hit the floodplain, if you will, right? You know what is the elevation above sea level from the DEM. Then, if you know what the elevation of every point within the flood, then you can get the difference between them is basically, if you kind of ignore maybe more complex hydraulics or fluid dynamics, you can get a good estimate of water depth in the scheme of things. The problem was, how do you extrapolate that in space, right? Because the floods can be very, very large. You have the whole slope of the floodplain. So the approach we took, the approach we took was actually, again, very simple one, a GIS-based approach. You identify the boundary of the flood from a polygon or a raster that you get from remote sensing analysis. You identify what we call the boundary cells. So all the cells that are at the boundary, right, the outside of the flood. You get their elevation from a DEM, very, very simple GIS approach. And then there's a simple mechanism to what I call inherent, or assign that elevation to the nearest cells within the flood itself. So it's a kind of a local maximum flood water, and it's all done within a simple Python script using simple GIS tools. Now we have a new, actually undergraduate research assistant. We're going to try to make it open source. This is based on our GIS ArcPy tools, which is nice, but it's not very computationally efficient, nor is it open, right? So we want to make it more accessible to people and make it more computationally efficient. It works really fast for small or coarse resolution, DEMs, but when you get to high one, which I'm going to show you an example, it gets quite slow. So this is from the paper itself. We tested this model against hydraulic simulations for both a 10-meter DEM of a large flood in the Brazos River in Texas, and then a 1-meter LiDAR DEM in a small flood in Lyons, Colorado, both real flood events that had real hydraulic simulation calibrated for them. And then we just compared our simple DEM-based approach to their sophisticated hydraulic-based modeling, and the results were actually really, really favorable. So it was actually a very, very nice result. That's why I say it's so gratifying, because that did work quite well. And if you think about it, there's no reason why it shouldn't work, right? Water, what I like about water, it's simple. It goes downstream, right? So it's predictable in a way. Obviously, if I say that to Fred Ogden, he's probably going to get mad at me, but there's a lot of processes, obviously, in hydrology and hydraulics. But in its simplicity, right, it's a relatively simple thing to work with, unlike atmospheric contaminants or whatever. That's much harder to do. Anyway, so this works quite nicely. I'm going to skip over that. We did some more test case studies, and I pretty much said that. Now, I actually used this tool during the 3 hurricanes, the big 3 hurricanes that we had, Harvey, Irma, and Maria. And the flood maps came from remote sensing analysis from different people. So you see here, actually, this is probably just visually the nicest example from Florida. And then, so we just applied this model. We got the 10-meter DEM. I remember, right, the Nook, I think you were the one that's like emailing, can you get me the DEMs for Florida? There's flooding going on. And it was actually very exciting times for me anyway. And then we can also do, this is looking at buildings. So we have all the address points for Texas, thanks to David Maidment and his team. And so you can just overlay the address points and over the water depth, and you get an estimate, a very quick estimate of building impact, right? How deep is that building, or how much water this building has seen? Now, obviously, it's not going to be as accurate as high-resolution hydraulic modeling or observations that are very, in situ observation, but it's a big overview. It's a really easy and efficient way to do this. For Puerto Rico, unfortunately, the flood map that we got was very, very limited. I don't recall why. Maybe we didn't have SAR data for that. It is a small island, so it's definitely doesn't show as extensive of a, and also most of the damage actually in Puerto Rico was wind damage rather than flooding. Now this is very, very recent. This is not published yet. I got invited to use this tool for a NASA funded project that looks at coastal resiliency or coastal hazards. And it's focused on the Maryland, Virginia area mainly. So this is Portsmouth and Norfolk as well. And they're very interested in that. There's a lot of military installations there. It's a very, there's a lot of subsidence going on, so it's a very vulnerable part of the country for coastal flooding. So my task in this project, or it still is to look at trying to apply this tool, this very simple DEM tool. And the problems with coastal areas are twofold. One, they're very flat, right? So the DEMs, they don't really, there's not much of a topography in coastal areas. The second thing is that water, unlike a floodplain, right, when your water are more or less within the floodplains, here you have this open-ended boundary, which is the ocean or the water, which has a zero or sometimes even negative, depending on the DEM elevation. So I had to redo or create a new version of FUDET called, I call it FUDET C for coastal, that basically remove the actual pixels that sits on the water or on the coast itself, and then ran the same calculation and compare it to high-end or high fidelity hydraulic simulation of using the storm surge. This is from a 2011 hurricane, the name escaped me right now, that hit that area. So we actually have some observation, but this is using tidal data with a hydraulic model to actually estimate flooding at that specific location. And initial results are very promising. Actually, it looks pretty good. It took me a while to figure out how to do this for coastal areas, but I'm actually pretty pleased. The only problem is this is a 1 meter LiDAR, and it's a fairly large area. So again, it's very slow to calculate. So that's not good. So I think the next emphasis is making this tool more computationally efficient. Well, this is just showing some building impacts and so on. Anyway, wow, good. I was afraid I'm not going to be able to cover everything. So this is all I have. Again, if you want to talk to me about something specific, I'll be happy to. And yeah, if you have any questions, I know it was kind of a machine gun kind of presentation, but yeah, I'll be happy to take any questions if you have. Yeah.
You can mention that happening in the math is very interesting. So actually my question is, you can know the depth, you can know the elevation before the flooding and after flooding, so you can calculate the difference.
Well, that will make it even easier. You know,
Yeah,
right?
and but you still don't know the channel depth.
Yes. Well, that's a good question. So the question was, well, I think two, right? You said elevation before and after is actually having a different DEM.
Yeah.
So that some floods, people actually go with a LiDAR and measure the elevation with the flood water in place, and therefore, if you do the difference between the before flood and after flood LiDAR data, then you actually don't need this, right? Because you have direct observation of elevation difference. And the other question was, there's no information about the channel itself, the bathymetry of so that's, you're absolutely right. It's underestimating. We have a case study in the paper when we look at the big lake. So this was Lake Houston, and there was a flood there a few years ago. And yeah, you know, we don't know how deep the lake is. So we don't measure, or we don't estimate, or we can't really accurately estimate water depth at the channel itself or at the lake or whatever water body we have, because we just don't know. But my argument was that it's not really important for us because this is a flood response kind of tool. So yeah, whether or not it's, you know, 4 meters over the river or 8 meters, it's still the river, right? It's the active channel. So we are mainly interested in the new water, right, the flood water. Yeah.
I have a question about flooding predictions. So I can imagine that infiltration rates in the fluvial system on the banks of the rivers and around the river itself would play a role into whether the river will flood further, the water will cover larger areas. And I don't know how, you know, how do you account for that, and how, and
This is not a prediction tool. It's a snapshot analysis tool. So someone give me a flood map, however they got it, right? From remote sensing observation, from very sophisticated modeling that account for all of that. And well, if you have the modeling, you don't really need to use this method because the model can give you that result as well. But however someone give you a snapshot of what's going on at that point in space, that's where it's become useful. So I envision this being useful either for near real-time flood response, right? The flood is going on right now. It takes quite a while to get a good hydraulic model calibrated for a specific event. So something that we need now, this is a tool to do it. Or if you try to do this for a very large database, like a US streamer, for example, we have 40 flood maps. If we try to start calibrate a hydraulics model that account for all the fluid dynamics, then that's going to take forever, basically, because it's very complicated. So either for volume or you know, rapid response, I think that's where this is most useful. Anything else?
For the delta model, you know, that there's so many complex variables there. I'm trying to understand how the predictions were made, you know, looking forward. What, did she take the observed current rate and then just move that forward, and were coastal currents and all of that accounted for?
She basically only accounted for what's coming into the delta. So it's actually not at all accounting for any processes, coastal processes. It's just trying to infer something about how much sediment is going to be getting into the delta from the river. So it's a river model. It actually has no delta component to it. And the way she did it, she ran this, I guess it was in there. She compared 2009 period average sediment into the delta to 90 to 2099, and then just compared the two. That was the way she did it. So that's how she came with those numbers. Anything else?